If you take an ice cube and let it melt into a puddle, you can always freeze it back. But if you leave a glass of milk out overnight and it sours, or if you bite into an apple and watch the flesh turn brown, there is no going back. In these irreversible scenarios, the original materials are actively dismantling themselves. Existing molecular bonds break apart, and the atoms recombine to form a distinct new substance. The simplest diagnostic test for this in daily life is permanence. Once the interaction happens, you cannot easily restore the material to its original physical state. Recognizing these permanent physical shifts allows us to identify exactly when the matter in front of us has been altered on a molecular level. To study how these transformations work, writing out long paragraphs about milk souring or iron rusting becomes inefficient. We have to translate these physical interactions into a concise mathematical language. This diagram shows the structural layout of a chemical equation. The starting materials, what we call the reactants, sit strictly on the left. The newly formed substances, the products, sit on the right. The center arrow dictates the specific direction of the transformation. Assigning chemical symbols to each element replaces descriptive text with data. This allows us to track exactly how many atoms are participating in a reaction at any given moment. This symbolic structure gives us the exact analytical tool required to predict how different forms of matter will interact and what they will produce. When you first write out a raw skeletal equation, it usually looks mismatched. Here, 2 separate atoms of hydrogen and 2 of chlorine go in, but only 1 of each comes out. This imbalance violates a strict constraint of physics, the law of conservation of mass. Because matter cannot be created from nothing or destroyed into nothingness, the exact quantity of atoms for every single element must be perfectly identical on both sides of that arrow. To fix the mismatch, we use the box method. You mentally draw a rigid box around each chemical formula, locking the identity of the molecule in place. You are strictly prohibited from changing the small subscripts inside those boxes. Doing so wouldn't balance the equation. It would invent a completely fictitious molecule. Instead, you apply whole number coefficients directly to the front of the locked boxes. You scale up the entire molecule until the total number of atoms on the right equals the left. Balancing an equation is a mandatory accounting process. It ensures that the chemical model precisely reflects the total mass conservation required by the reaction. Despite the millions of possible ways chemicals can interact, their mechanisms sort neatly into 4 predictable architectural patterns. In combination, elements merge into a single compound. In decomposition, a compound breaks apart. In single displacement, a highly reactive element forcibly evicts a weaker element. Finally, double displacement is a mutual exchange of ions, where distinct compounds trade components. By filtering any chemical interaction through these 4 architectures, you strip away the complexity and can predict exactly what will emerge from the reaction. This illustration shows a rusted iron beam next to a pristine one. The pristine beam is protected by paint, which acts as a targeted barrier. It physically blocks atmospheric oxygen and moisture from interacting with the iron, stopping the corrosion reaction before it begins. The same principles apply to food preservation. Manufacturers flush sealed chip bags with inert nitrogen gas. Without ambient oxygen present, the fats in the food cannot rapidly oxidize and spoil. Understanding these mathematical patterns makes the physical world more predictable. By identifying the specific reaction type and balancing the inputs, we can anticipate and manage the natural decay of the materials we use every day.